same kind of concept with like limits from coming from the right and left?
No, it's not even that complicated. No, for some reason, the limit notation tends to make things more complicated than they need to be. This is really just saying if you know that z represents a set of integers, then a little plus after it means that you're only focused on the positive integers. Right? If it has a little minus after it, you're only focused on the negative integers. Right? So what we're going to look at first are sequences, because sequences have finite endpoints. When you get into a series, that's when they can go on infinite. So when you get into infinite series, that's when things get interesting. But in order to understand a series, you need to understand a sequence first. Because all I have to do in order to take a sequence and make it into a series, slap a little summation symbol onto the front of it. All right, but we'll get there. All right, so a little notation here. N belongs to the set of positive integers. All right, n greater than or equal to n, where capital N represents a specific positive integer. All right, very interesting notation. All right, we've worked with functions of a real variable, and so the domain is either going to be a set of real numbers or a subset of a set of real numbers. So that's good news. All right, it doesn't seem like, based on just reading all of that it would be good news, but it is, because what this is telling us is that the numbers that we're working with are familiar. I'm not changing the rules of the game. I'm not going to throw imaginary numbers at you now or anything more complicated, right? And in fact, personally, I think all of that stuff there is to justify the fact that we're going to use the letter I as a variable. They could have just chosen a different letter, like J or possibly K, but they elected to use I very frequently when it comes to a sequence or a series. And because of that, there became a lot of confusion. Wait, is this the imaginary I, as in the square root of -1? Or is it some other I as in a variable? All of that is to tell us that we're working with I as a variable whenever I comes up. All right? So, consider the sequence. All right? I've officially considered it. Well considered. Basically, if we have f of n equals the square root of n plus 3, all that's telling me to do is evaluate the function. If I'm only looking at the positive integer values, I'm evaluating the function for all possible positive integers. All right? Problematic, definitely. Because I can't just keep going. I'm going to run out of life. All right? So we need to come up with some way to represent this. And so that's where the notation comes into play. Okay?
I heard some little kid was one.
Gauss. Carl Friedrich Gauss. Yeah, it was, I mean, the different variations of the story, but I mean, I kind of took the real version of it and fictionalized it, because I like my version of it better. And so, a teacher gives an assignment to the class, and Gauss works through the assignment quickly, gets the answer. It's a number calculation. Very, very mental math, possibly heavy, where the students they'd have to show some work in order to come up with an answer. Like, we've all been in that situation where you got an answer, you put it down on paper, and you lost credit because you didn't show any work. And you're like, well, why didn't you show any work? It's like, because I didn't need to show any work. And then, a wise guy like me would be like, well, I figured it out in my head. And then the wise guy like me as the teacher would be like, well, that's too complicated for you to do in your head, hence the need for you to show work. And then I would challenge that individual with a similar problem, which they would immediately get wrong. But anyway, so Gauss was put in a position where he had to essentially prove himself. So he got the answer very quickly. The teacher said, oh yeah, wise guy? Well, figure out this one. Add up the numbers from 1 to 100 and do that as fast as you can. So figuring that Gauss had to at least get out a piece of paper teacher was wrong. Gauss went back to the desk for a sec, considered the problem, came back to the teacher with the correct answer, 5,050. The teacher then started looking for cheating devices. You know, it's back in the Stone Age. I mean, it was not, but in my mind it was. Like the hidden cheat tablet, not like iPad tablet, but I'm talking about like a stone tablet with like notes etched on it, with like a hammer in it and a chisel. That would be the equivalent of a note card. You see, there's all stuff that goes on in my brain. And so teacher's looking under the desk for all the notes that must be there to get the answer, even though how could he have predicted what question would have been asked? And so it was at that point where Gauss actually came up with one of the fundamental aspects of sequences and series. And so what he did was he was clever, said, okay, I got to add up the numbers 1, 2, 3, 4, 5. I might be stealing my own thunder here. This might be actually written in there somewhere. And so on, all the way up to 100. And it's like, and you know, that even the great ones, they had to do some trial and error. So he probably started adding them up. 1 plus 2 is 3, plus 3. This sucks. There's got to be an easier way. All right, let me try going the other way. 100, 99, 98, 97, 96. All right, that sucks too. There's got to be another way. Then he starts looking at it this way. Well, what if I just add up these pairs? Oh, wait a minute. I might be onto something. For every corresponding pair, there was a sum of 101. How many pairs were there? 50 of those 101s. And so we get a product of 5,050. I mean, some of us are impressed by the fact that he could do 50 times 101 in his head without a calculator. First and last.
Yeah, 1 plus 99 and then 5.
It isn't much. Yeah. Honestly, I mean, I've read the true tale at one point, and my fictionalized version is what dominates my brain. So somewhere in there is the real story, but I can't get past my tablets with the chisel and the hammer and all that good stuff. And so yeah. But anyway, how does this connect? Well, you know that you have a sum starting with the first sum going to the 50th sum of the number 101. Basically, the number 101 written 50 times and added together. That's what this means. So, where does that come from? Well, that's a different story. Say it again. When you get the first 50 values, then the second 50, there would be some pairs. What's that?
Yeah, it's 49. So there's 49, up to 49.
Let's count 0.
50, and then there's...
Oh, then
That's why I was like, it's
Yeah, it's 99, it's not 100.
It's not
1 to 50 and then 51 to 100.
51.
No?
Oh, yeah, you're right.
Yeah.
That makes sense.
No, the 100 is the 1 and the 100 are the only things that I think we all agree on. No, this one goes to 50, and then it wraps around going 51 to 100.
Yeah, you're right, you're right.
Every now and then, you know, broken watch is right place. So, unless it's difficult, in which case it's never right. Yeah. So, that's my little Gauss story, or my little fake Gauss story. But anyway, I think it's infinitely more entertaining than a real one.
Wasn't he like a kid would be like figuring this out or something?
Yeah,
Yeah,
yeah.
I forgot about this one. Nuts.
So in terms of notation, all we're talking about when I say f of capital N is a particular n value in the sequence, starting with n being lowercase n being greater than or equal to some particular value. All right. So the way that would play out, and this is just to get a feel for how things go. This would be f of 1, f of 2, f of 3, and so on. So the last entry, though, is actually the weirdest one, because this one I'll actually show the intermediate work. The other ones I took it on faith that you wouldn't need to see it. 1 plus n minus 1 would become, when you clean it up, f of n. All right, I'm missing, a little typo bonus for somebody. There should be a comma there. And I get a comma there. And actually, I don't think I need to wait anywhere near as many of those dots, just 3. And then we can continue on and on. It's just typically we designate n as the stopping point, even though it could represent some infinite value, in which case we wouldn't actually stop. Okay? So, just for convenience sake, we write f sub n, but we're not even going to write that very often. All right, when we designate functions, it's not anything new to you. We typically start with f, and then go to g, h, and k, and then after that we start making stuff up, because if we're working with more than 4 functions at a time, things are starting to get a little crazy anyway. And then the most common names for sequences are a, b, and c, because those they're going to sort of take the place of a constant within a function, even though they won't themselves be constants. They're going to vary. They kind of work the same way, where you're going to plug whatever you have as your function for a, b, and c into your functions for f, g, h, k, whatever. All right. So the domain of the sequences, and then the first 4 terms of the sequence. Sometimes you want to do this part first. All right, the first 4 terms of the sequence. So I replace n with a 1 to designate the first term of the sequence, in which case I'm looking at the 4th root of 1 minus 4. All right, so that's a problem. Let's keep going until it's not a problem. Well, at least this one time anyway. 2 minus 4. 3 minus 4. Then in a different color, I'm going to go to a sub 4 is equal to the 4th root of 4 minus 4. All right, so it took those first 3, we'll call them misfires. Not really, they're more like learning experiences. Each one of these are imaginary. So my sequence doesn't actually start there, because I'm only working with a set of real numbers here. All right, so anything imaginary is out. So those first 3 I would ignore. Those would not count as the first 3 terms of my sequence. But now, not only am I going to get the first 4 terms of my sequence, I'm also going to get a sense of the domain, because this is telling me that my n value has to be greater than or equal to 4. All right, so I have my domain. All right, then in terms of the sequence, I'm going to get a 0, a sub 5. Some of it you can do in your head. Some of it you're going to want to leave in radical form. Very rarely are you going to want to go to calculator in lieu of a radical. All right, there's some circumstances where you might consider doing that, but they're very rare. So like, for example, this is the fourth root of 2. Right? So we'll write the fourth root of 2. We're not going to go decimal on this just for convenience sake. Right? And in fact, you may not even want the radical. Maybe you just want to write it as 2 to the 1/4. I think that's a little nicer. All right? A to the 7, A to the 7, A sub 7 would be the fourth root of 3. So I'm going to write that as 3 to the 1/4. All right? So, technically, I suppose, I've done what the question asks. But very often what they're looking for is a nice, simple way of representing your final answer. And so the way I would write it, under normal circumstances, I wouldn't show this work, I'm just doing it for instructional purposes, I would write a sub n equals 0, comma, 1, comma, 1/4, not 1/2, much as I want it to be. And then just make a statement. N is greater than or equal to 4. But really, since I only want the first 4 terms, I would actually specify, that's supposed to be a semicolon, by the way. I know they always look like J's. I can't do it right. It's like my one kryptonite. So, that and apparently pacing. So, one of my strengths is sarcasm. Since I'm going out 4 terms, my 4th, 5th, 6th, and 7th, I would actually personally like to make that clear. All right, what I wrote in blue answers the question perfectly fine. What I wrote in red is a nicer answer. All right. Both full credit. You don't lose points for either variation of it, but yeah, it tells a complete story. What I wrote in red tells a complete story. You know, anybody who has even the slightest bit of experience with this will look at what I wrote in red as, oh yes, I see exactly what you're talking about. Whereas the blue, it's like, oh, it's a lot of stuff to tell me what you're saying in red. All right. Now, number 2 is very similar. The idea again being that you need to identify any trouble spots, but just listing out the first 4 terms often will designate those trouble spots. So, for example, just looking at this one, I would say that n, I don't want this to make my denominator equal to 0. All right, but just by looking at it, the only way that's going to happen is if n is a fraction. Well, n has to be a set of positive integers. So it can't be a fraction, which means I'm looking at a domain that would be the set n belongs to the set of positive integers. You just leave it at that. All right, if you recognize it off the bat. If not, you kind of start diving in and see what's going on. B sub 1. That's a clean 5. B sub 2. So I'm plugging in a 2 now. So I'm going to get a 6 over, what was that, 4? So 3/2. You want to pick and choose under what circumstances you simplify a fraction and what circumstances you don't. The reason why is sometimes if you have to determine a pattern, if a pattern exists, sometimes in its unsimplified form it's easier to see. So 7. Sorry? We only started with 4 because the first 3 entries, 1, 2, and 3, gave us a negative under a radical, so they were all imaginary. These are not imaginary, so they're fine.
I'm talking about the second problem.
Yeah. That's why I started with 1 in the second problem, because there's no value that will make it imaginary. There's no radical. You were asking why I didn't start with 4, yes? Yeah. there was no need to. I started with 1 here. It just gave me negative under radical, negative under radical, negative under radical. So I ignored all those. The next one in the sequence that made sense was 4. So I continued from there. The first 4 values actually work. Here, right off the bat, if I plug in a 1, I don't get anything imaginary, so we're good to go. Yeah, we start with 1 unless we have reason to choose something else.
For example, the 4 root of 5 minus 4 is not 1 and a quarter. 1 to the 1 and a quarter.
1 to the 1/4, which it would be 1 also, because 1 to any power is 1.
And
But you could leave it as 1 to the 1/4 if you want.
And the second one, it's not 1, it's 3. 7 over 7 is not 1.
Oh, I haven't gotten there yet. You had a question right mid-prop. So I plug in a 3, I get a 7 on top. Plug in a 3, I get 7 on the bottom. Result gives me a 1. All right, and then B sub 4, I'm going to get 8 on top, 10 on the bottom, so 4/5. All right. Accomplished the goal, it looks like. All right. Now, what I would say here, if I wanted to write it in the other form, I would say B sub n would give us the sequence of 5, 3/2, 1, 4/5, specifically if n is between 1 and 4. I shouldn't box it. This is just as good as the other way. Because of this. All of this is related to that. That's the main idea that we're building off of.
Yeah.
Yeah, every single time.
How do we know that?
How do you know?
That it's there. Like, for instance, if I'm looking at problem number 3 and just see this, if I just see problem number 3, how do I know that that's what it's referring to? Or is it just because of the n and the how it's formed?
Well, we're always starting with this. We're going to limit from here.
Okay.
So our domain, if there isn't any value of n that'll make it imaginary or undefined, this is what our domain's going to be.
No matter what.
No matter
That's
what.
standard.
That's the standard.
Okay.
That's our real number system for
Okay.
this unit. All right. But in number 3, we see that there's a value of n that'll make it undefined.
Yes, of course.
So then we have a problem there, and that problem would need to be addressed. That's the thing. So it's a question of,
We don't care.
right, if it doesn't matter for the problem, then you're fine. But if we needed to expand beyond that, we'd have to take note of it. They are asking us for the domain. So the domain is n such that n cannot be equal to 6. All right. Now, technically, it should be n belongs to the set of positive integers such that n cannot be equal to 6. I think that might be a little overkill. If we all know that we're working with a set of positive integers, I'm not going to then be a jerk, turn around and say, well, how do I know that you weren't talking about negative 32 as being part of the set? So, because it doesn't work. So if you write this, it's fine. If you write, I mean, if you want to go interval notation, you're welcome to do that too.
So that's the question.
Brackets include, parentheses exclude.
No. Difference between C and N? Is C like the notation and N like that? Or do they mean the same thing?
N represents a variable within the sequence. It's actually, I mean, when you think about, it's not a true variable, it represents the position within the sequence, which is why we stick to the set of positive integers. Because if you think about like a person's position online, like I line up a bunch of people, I'm not going to say that a person is occupying the 0th position or the half unit position. You're either in the first position, second, third, fourth, fifth, and that's where we go. What this is saying in this particular problem is that there's a manhole at the 6th position if you try to stand there. Because that's a set of real numbers, and that allows for fractions, decimals, negative numbers, all hell breaks loose. Okay. The N, the capital N, actually represents natural numbers. So natural numbers and positive C, they actually mean the same thing. It's just people tend to not know what the hell anybody's talking about when they use a capital N as opposed to a lowercase n. So what is this? It's actually a natural number within the sequence. So it's kind of strange. The origin story behind the notation is probably more interesting than the notation. Why? Oh, I looked that up. Yeah, but it was
Because no one else uses it.
no, there was a reason. I had a student research for it. Oh yeah, it's German.
Well, that makes sense.
Yeah, that's the explanation for everything. It's a German word for number, Zahlen, Zahlen.
Really, that's it?
Yeah. Now, why that? I mean, if it's really just, well, I don't think it's the German word for number. I think they're saying a German word for number. Number, numeral.
What a boring reason.
Why they pick positive numbers to work with?
Because we're talking about a position within a sequence. So your position can't be a negative number. Like if I had, I could even go like items in a classroom, number of desks or chairs. If I had them all lined up and if I were to actually go around and actually count the number of desks in the room, 1, 2, 3, I wouldn't say -1, -2, -3. Even if I were to remove a desk from the room.
But which sometimes we have fractions, sometimes.
Sure, but that's the result of the calculation. What we're looking at for n is the position of each of these calculations within the sequence. So n being 1 tells me that the first result of this fraction is 5. When n is equal to 2, that means the second result of this calculation is 3/2. So it's kind of boils down, or back anyway, to the Riemann sums when we were putting the rectangles inside the curve to approximate area. N represented the number of rectangles that you could squeeze into that finite space. Right? So I could put in 30 rectangles, I could put in 50 rectangles, I could put in 2 rectangles. I can't put in -5 rectangles. Right? There's no context that allows for that. Right? So the result of it is not what we're talking about in terms of value of n, or even the domain. The domain is just talking about what type of number n can be, independent value within the sequence. And since it's only talking about position, we're only talking about what are called discrete values, countable values. Negative numbers don't come into play, fractions don't come into play, decimals don't come into play, and so on. Right? Pi, things like that. So in the case of number 3, I can't put a 6 in there, but since I don't need it, it's immaterial. I just need C sub 1, 2, 3, 4. All right. So the first thing we want to do, and this is probably the most important thing in the early goings, is to try to get a sense of what this part of it represents, because the other part of it is pretty easy. It's just plugging and chugging. But -1 to a power. All right, if I take -1 and raise it to an even power, what kind of number do I get as a result? Get a positive number. If I take it and raise it to an odd power, what kind of number do I get as a result? You get a negative. All right, so this is telling me that depending on the value of n, I'm either going to get a positive number or a negative number. All right, so I'll write it out. -1, oh, crikey. That looks just awful. -1 to the first, -1 to the second, -1 to the third, -1 to the fourth. All right, so just based off of what you see there, you can determine the quality of the number, the resulting expression. It's either going to be positive or negative. But then we also have the other part to worry about. If I plug in a 1, I'm getting 3 on top, and I'm going to get a -5 on the bottom. Right, so -3/5. If I plug in a 2, I'm going to get a 7 on top and a -4, so -7/4. All right, if I plug in a 3, I'm going to get 11 over -3, so -11/3. All right, and then if I plug, I screwed up.
Yeah. First positive.
3 minus 6, -3.
I'm just focusing on this guy right now. So they're right? Okay. All right, so it's kind of important here because they gave us a model to work off of, but that model is, I mean, it's good, I guess, but it doesn't tell you the whole story. The whole story comes from the idea that we kind of feel out the data. So I mean, I'm pretty confident anyway that I can figure out, without looking back at the fraction that was given to me, I can figure out the numerator and denominator. I see the pattern. The denominator is decreasing by 1. My numerator is decreasing by 4. All right, consistently. So this next one would be -15/2. And you could verify it. It's not going to be too crazy to verify, but I mean, it should bear out. So anyway, -1 to the first, that's our negative result. 2 negatives give you a positive, 3/5. Anything to an even power is irrelevant because it's going to become positive. So that's just a -7/4. And then a -15/2.
Wait, the second one, the 6 of 2, is not -2/4? Because it's 2 minus 6 is -4.
For the second one?
Yeah.
2 minus 6 is
4 minus
-4.
2, 4 minus 6 2, yeah. So the numerator, the denominator is 2 minus 6 will be -4.
4 times 2 minus 1?
No,
I mean, that's what it should be.
the denominator will be 2 minus 6 will be -4.
Right.
So that would be 2 over -4, which would mean -2/4. No, am I right?
4 times 2
Yeah.
is 8 minus 1.
Oh, you just should. So
It's got the 1 and 2 backwards, I think. All right. -1 times -11/3 is going to become positive 11/3. All right. So that's our mini expansions. 3/5, -7/4, and so on. All right. But, you know, you can imagine that this idea of recognizing the pattern becomes more useful if, I mean, they only ask you to go out 4 turns. What if they ask you to go out 20 turns? What if they ask me, whoever they are, to identify just the 20th term? Then what? I need to solve the point here. But, you know, the classic question would be, here's the first three terms of the sequence. Now identify the 15th. You can make an equation, but if you notice the pattern, it's really just a matter of subtracting. All right? There are some techniques that we'll use to write equations. Some of them are easier than others. All right? But this is the foundation of something called an arithmetic sequence. All right? Where the only difference, and we'll formally discuss this later, but the only difference between consecutive terms of the sequence would be, well, a difference. So you're either adding or subtracting something. All right? The alternating part of it makes it funky, but I can get to the absolute value of one term of the sequence from one term of the sequence to another just simply by adding or subtracting. Sometimes the only way to get from one term of a sequence to another is by multiplication or division. So this is the basis of something called an arithmetic sequence. I remember looking at it, that word, the first time, assuming that my spelling is sufficient enough to actually get it out. I couldn't not see the word arithmetic. But in this context, it's pronounced arithmetic. I don't know why. I don't know why. I'm sure there's a fascinating reason. But movement from one term to the next is only through addition or subtraction. All right, addition or subtraction. Now, again, we have the alternating component of it, so it's not, I mean, in and of itself, it's not fully an arithmetic sequence, but it does have the basis of it. Right? If I ignored the part where we have -1 to a power and just focused on the meat of it, that part would be arithmetic. All right? And down the line, we'll have to distinguish from one type of sequence to another. Now, the next question, you know, they didn't designate it as anything. They just gave us the set of 3 over 10 to the nth power. Now, there's no value that no positive integer that I could plug in for n that would make it imaginary or undefined. So my domain would be n belonging to the set of positive integers. So 3 over 10 to the first, 3 over 10 to the second. I'm writing it slightly differently here. It may seem like I'm doing it massively differently, but really not. I'm doing the essence of what I was doing in the previous questions, just in a different format. Because they didn't designate this as a particular model. They didn't call it like d sub n equals this. This is representing a sequence, and we just need to identify the entries of the sequence. Right? In a lot of cases, what I just wrote down would be sufficient. Sometimes we want the decimal, but sometimes we just want the fraction. And I would wonder, what's the benefit of writing it, well, let's start with writing it correctly. You know, 3 over 10,000. All right, not terrible. Make that power of n any larger, and it starts getting out of hand pretty quickly. All right, so this would be the set of the terms of my sequence. And I could put it in decimal form, but it would beg the question of, okay, well, what's the benefit of that? Maybe 0.3, 0.03, 0.003, 0.0003, and then keep, well, actually that would be 4 O's. So You just keep putting in more zeros, and eventually you get into scientific notation, at which point you're just basically writing this stuff again with negative exponents. So oftentimes what I wrote in black is sufficient because you're not really getting anywhere by going any further. All right. So then a natural follow-up question might be something like, hey, could I do any of this on my calculator? Good question. Oh, you'll see. No, actually, I have a real answer. This is the basis of infinite sequences and series, which is basically us working with the algebraic forms, not the numerical forms. What happens is, and this goes back to the Taylor polynomial stuff, it's the tech assignment. I don't know if you had a chance to see the overview.
I've looked at it again.
Yeah, when you get really deep into that, you'll see a little bit more clearly what I'm talking about. But basically, we have the ability to represent functions that are not algebraic, like trig functions, log functions, and so on, in terms of algebraic functions. The issue is, in order to make them precise, we have to go out to infinity. So in the tech assignment with the Taylor polynomial, we only go out to the third derivative. So we'll do total of 4 terms of the basically the series. Okay, so we're taking, I mean, this is basically this, just with the Taylor model. Right, so we have this, whatever this result is, plus this, plus that. That expression will model part of a trig function or a log function or whatever. The more terms I include, the more precisely it models more of the graph, right? Meaning, if I can get out to an infinite number of terms, so if I can get actually infinitely many terms in my series, then my polynomial model would be identical to the trig function in its entirety. What's the benefit of that? Very easy to take the derivative of a polynomial function. Not as easy to take the derivative or antiderivative, because, I mean, I don't know about you, but it wasn't always there when I needed it. Like the antiderivative of secant of x, or the antiderivative of even the tangent function. I mean, does x ln x minus x pop to your brain immediately? Sometimes. Would I want to? I'd love to.
It goes to infinity, and then you die.
Oh, no, I'll be fine. Because you know how, no, not even. So you know how, like, by expanding out the first 4 terms here, and it didn't take us 4 terms to do it, but you get a sense of what the pattern is. So what we're going to do is we're going to get a sense of what the pattern is in the derivative of just a small expansion of an algebraic sequence or sequence. All right, so this, what we have here would be in terms of x. And then from what we see here, we can take the derivative of each part and get a sense of what the pattern is there, and then work backwards to come up with this model. And that model itself would represent the antiderivative. All right, it's kind of hard to wrap your brain around in the early goings because we do have to build up to that. And I'll tell you, even as a student, well, definitely as a student, but even in the early goings as a teacher, it's oftentimes not that easy to wrap your brain around. Wait, that works how again? And then you develop a little bit more appreciation for the people who actually invented this stuff.
The connection that I can see is with the rectangles underneath the when you're trying to approximate an area of the graph.
And that's a good connection. That's a really good connection because that's actually the beginning of what we're going to be using, because that's the idea of an antiderivative itself. Like, I mean, the concept of an antiderivative, it used to be taught without any of that rectangle stuff. It was like, just find the antiderivative. And then by the time you get to, like, maybe the early goings to Calc 3, it was like, oh, remember how you learned how to find an antiderivative? Well, this is why it works. And then it would be this introduction, we draw some rectangles, and then we go from there. So, but the idea here is that we're going to actually take antiderivatives of functions that are already in and of themselves defined in terms of a sequence or a series. right? So it's kind of a inception. Not really, because it's already built in there. So, but here's the thing. I don't know if you've seen the movie Inception. It's a great movie. Or Interstellar. Or I can name any Christopher Nolan movie. If I were to tell you what happened in the last 5 minutes of the movie, 10 minutes of the movie, it would be a spoiler, obviously. But more importantly, you'd have no idea what the hell I'm talking about. Because you hadn't been set up by watching the first 2 hours and 15 minutes of it. Right? So I know what we want is the end game, the sense of, okay, where is this all going? But I'll tell you, if you don't have the basic vocabulary down, it's a lost cause. So let's get a little bit further in and get a handle on believe it or not, this is the basics. And then it'll all start to kind of coalesce, and when it does, you'll start to understand what I'm saying. All right? And I won't, that big aha moment, I don't rush through it. It's a nice moment for everyone. So when it happens, we'll take a moment and enjoy it. All right, but before we get to that calculator approach, there's a few different ways to handle it. Most people are pretty affectionate towards this method. Second, stat, ops, 5. Second, stat, ops, 5. There's other methods, but since we're learning about sequences, it's kind of nice when there's a function that's built into your calculator that's called sequence. Odds are it's going to be the right way to go. So again, second stat over to ops, option 5. EXPR stands for expression. So put in the expression that you're given. I don't know if the alpha tools work here, but let me try it. I haven't done it in a while. No, it just brings a fraction bar. So type it in, 3 divided by 10 raised to the, you could use n, you could use x. I mean, we're using n there, so I might as well. The only thing is they don't have lowercase letters for every letter in the calculator, so odds are you're going to be using a capital N, which technically means something else, but we'll live with it. Tell the calculator what is the variable, because if your answer is supposed to be in terms of a variable, it would need to know that. My variable's n. I want to go from the first term to the fourth term. The step would be the increments. All right? That's because the calculator can use the sequence function for a lot of different reasons or different uses. Okay? We are using it only for positive integers. And in fact, it's intended to only be used for positive integers. However, in a stat class, actually, I mean, you could even make a case in a trig class. Maybe you want to go by half units or pi over 6 if you're thinking unit circle. If you're not changing the step, if you only want to go by integer values, leave it blank. If you're really paranoid, put a 1. You don't need the 1, but just in case, you can pop it in. This is what comes up on your home screen. Function, variable, start, stop, step. Enter. You don't like that form, right? Okay, math, enter, enter. See, even after the fourth term, the calculator gives up and says, forget it, I'm not writing those fractions anymore. I don't like it. So now if I had to go out to the 20th term of the sequence, I don't see how that would be any more complicated. Now, if you want to, because 20 terms is a lot to scroll through, so let me show you real quick. We'll just go up. Instead of going to the fourth term, I'll go to the 20th term. Like I said, I don't need the step if it's other than 1. So I can do that. It'll give me 20 terms, but now, like, how do I get over there? Scroll. That's going to take forever. So what I can do instead of doing that is store it into a list. So I'll just store, let me hit enter, that with store into, so the store key, and then put it into L1. It seems like nothing happened, but when I hit stat edit, it stored all those values in L1. It's a whole lot easier to keep track of things. And I would even say that, I don't think I'm lying. I think I'm telling the truth there. Yeah, sometimes I say that it's a whole lot easier to do it this way, but I'm not really telling the truth. I'm justifying the fact that I'm showing you how to do it a particular way. But here, I think I am telling you the truth, because if I needed the 7th value, I don't have to count. It keeps track of the count in the list menu. So if I wanted the 7th value, for example, just look for the one that has 7 in the parentheses, and I have it. But again, like I said, after a certain point, the calculator stops representing it in a fractional form or even a convenient decimal form. It goes over to scientific notation, in which case, it begs the question, why did I write it in any other way than this to begin with? Also, once you have a sense of this sort of thing, you don't really need to list out terms in order to figure out what the 20th value would be, because it's clear that it's going to be 3 over 10 to the 20th power, just based on the nature of it. What we will run into is the idea that, well, maybe I want to add up those values. Maybe I want to add together the first 4 terms of the sequence. Then what? Well, if that's the case, might be in for a little bit of a ride. However, the calculator has a sum function also. Okay, so I might want the sum of my sequence also in the second stat menu over to math. We'll cross that bridge in a few minutes, but it's good to get to know your calculator. Let's just put it that way.